I hope it's not laggy this whole time. Okay. All right. I think we finished chapter 6 last day. Oh, you tell me. I don't know. We did. We finished chapter 6. So we're moving into chapter 7. Chapter 7 is on interactions. We've seen interactions before. It is actually. So chapter 7 is on interactions. We've seen interaction terms before in regression, right? When we multiplied two of the predictors, right? So in regression, we saw interactions. We saw interactions, things like x1 times x2, or I guess maybe I'll use capital X's. X1 times x2, right? That kind of thing. We're doing the same thing here, but what's different is that in regression, we just kind of, we tried it as an option, right? We said, okay, maybe there's an interaction here, and we just kind of put it in as a term, checked it out, see what happened. In ANOVA, we're gonna have more structure to when we use interaction terms and when we don't. And so in ANOVA, we have more structure / methods. I guess I'll make it plural, although they're the same sort of. In ANOVA, we have more structure / methods to determine if we need an interaction term.
So we use interaction term when you know x1 is dependent on x2.
Yeah, but I feel in regression we just kind of tried it, right? If we felt like there might be an interaction going on, right? Like one might depend on another in some way that we maybe don't know about or we do know about, right? But here in ANOVA, it's going to have the same thing. It's going to be the same thing, right? Two things are interacting, right? But we actually have methods and graphs and things that we can look at to say, I have to use an interaction term because this is going on here, right? And so, and I know you guys like that kind of stuff, so no, just try it. Wild, wild west out here. So in ANOVA, we have more structures / methods to determine if an interaction term is required. Okay, so we'll talk about those, but beyond that, there's nothing really new going on in this chapter, right? Chapter 5, we established all these general ANOVA methods. Chapter 6, we introduced, okay, now I actually have 2 factors. Did I hear something? Oh, okay. No, I just thought I heard myself echoing. What echoes in here? So in chapter 5, we established the basics for ANOVA. Chapter 6, we said, okay, well, now I'm going to introduce another factor, right? So now I've got this 2-way ANOVA. What do I do here? I've got a blocking term. I've got a treatment term, right? And so, but beyond that, nothing really changed, right? It means I'm gonna have a treatment effect and a blocking effect, but the ANOVA and everything that we do around it kind of stays the same. Now, the only thing that we're adding is this interaction term, right? And so everything else stays the same, right? Checking to see if your standard deviations, are they roughly the same, right? So you're going to check that ratio. Do I need a transformation? That kind of thing. And so everything else that we've learned, we're just building on that. This is not a new thing. It's just an addition. So the only new thing is the interaction term. So an interaction term is if there's some sort of, well, I guess interaction, but also some sort of dependency in our factors. And so interaction is if there is, I'll put it in quotes, dependency between our two factors. One thing that's kind of new is that in the past we've been saying, okay, we've got one observation per cell, meaning we only have one observation per treatment per block, right? And so now what we're opening up for is multiple observations per treatment per block. And so in order to have interaction, right, between two factors, in order to have interaction between two factors, right, and I'll just put in brackets, the two factors are typically a treatment and a block. Treatment and a block. Could be two treatments, right? I don't know, depending on the situation, typically. But what we've seen so far, two factors have been a treatment and a block. So in order to have interaction between two factors, we must have more than one observation per cell. We must have more than one observation per cell. And a cell is a combination of the block level and the treatment level. And so if we've got our, I know I had to change them. It doesn't matter which one's in the rows and which one's in the column, but I feel like we put our treatment here. So if I've got 1, 2, 3 different treatments, and I've got 1, 2, 3, 4 blocks. Let's make this thing huge. That's a cell, which, I mean, you would probably land on by yourself, right? A cell is going to be a combination of a treatment and a block. So all those are cells. So before we were saying, okay, we only have one observation in each of these cells. Now we're saying, okay, well, in order to establish an interaction, we have to have more than one treatment per cell. In fact, we're going to say that we need a balanced design, right? So a balanced design is when we have the same number of observations in each of the cells. In fact, we will need a balance design to establish interaction right? And a balance design is the same number of observations per cell. Oh. Good. So I stole this kind of summary for all the terms that we're going to be using from the book. So a factor we know is a predictor variable, right? Which is a categorical variable, and so it has multiple levels. Two or more factors are crossed if every possible combination of factor levels is present in the design. We've been assuming that all our designs are crossed, right? Because we've got this kind of interlacing going on, right? And so we're saying that these things are crossed because there's no cell that's empty, right? We didn't, not put any of treatment 3 in block number 4 or something weird like that, right? We're interlacing and we're assuming that we have, we're looking at all the possible outcomes with these two factors. And so each combination of factor levels is called a cell, which we just established, and a factorial design, and they kind of sneak that under the radar, factorial design, but that's just when we've got these factors, right? And so that we call that a factorial design, is balanced if it has the same number of observations per cell. So a two-way factorial design crosses two factors of interest, of course, and so that's what we've been doing ever since chapter 6, where we introduced that blocking term, right? And so we can move away from the blocking term and look at two treatments, but often it'll be, a block and a treatment factor. And so in order to measure interaction, you need more than just one observation per cell, and the effects of the factors that get crossed, we call those main effects, and then we've got the interaction effects, right? And so now we're going to tack on that interaction, and just for terminology, right, we use the main effects and the interaction effects. So the main effects, treatment effect, blocking effect, interaction is how those two interact. All pretty okay terminology, right? But it's nice to just have it established. Okay. Any questions so far? All right, I'll let you chew instead. So how do we know if there's an interaction going on here? What we do, and now this is a little bit different from what we've been saying, right, is that now we have to have more than one observation per cell. So that means that we're going to have some, some sample size in each cell. And let's for a while assume that we have a balanced design, right? In fact, for interaction, let's assume that we have a balanced design, meaning we have the same number of observations per cell. So what happens is if we've got some sample size in each of these cells, like let's say we've got 5 observations per cell, then I can take the mean of those, right? And instead of looking at this extreme example, let's look at a 2 by 2, right? Just 2 levels for the treatment, 2 levels for the blocks. And so here, we can consider, it'll extend to a larger one, but just to establish what we're doing here, we can consider a two-way factorial design with, what is that? So we can consider a two-way factorial design with 2 levels per factor for simplicity. Oh. So if I've got just 2, oh. I've got some treatment A and B, and I've got some block 1 and 2. We could make up some numbers here, but let's say that we just calculate the means of these things, because I don't want to make up, 20 different numbers on the spot here. I'm not very good at making up numbers, but that's a human thing. We can't make up numbers on the spot. Random numbers, no, we're not very good at it. So let's say here, I've got some X bar and I'm in row A, column 1. Yeah. And let's say we have a mean observation here of 5. In here, I've got X bar, row A, column 2. Let's say I've got a mean here of 15. Both from treatment A, but in block 1, I've got a mean of 5, and in block 2, I've got a mean of 15. Now, moving on to B, right, treatment B, maybe I've got an X bar of B1, right, in block 1 of, I don't know, whoa, I don't know, let's say 7. And then I've got X bar of B, treatment B, block 2, and I've got a mean of 10, let's say. So the interaction, there is an interaction if there's a difference in the differences. I know. There is an interaction effect if there is a difference in the differences. And I'll put that kind of in quotes. And I want to show you what I mean by that, because that's not obvious, right? So the difference here for treatment A, going from block 1 to block 2, is going to be 5 minus 15. right? Putting me at -10. Or if you want to do positive, it doesn't matter as long as you're consistent, right? Because the positives and negatives are going to matter. If we go for treatment B, right, we've got a difference from 7 to 10. Right? And so I guess it makes more sense to have a positive difference. Right? Because I'm going from 7 to 10. Doesn't really matter, right? But maybe I should make it positive just to, what do you guys think? Like I said, it doesn't matter as long as we're consistent. Moving from 5 to 15.
When it's more important what you say, when it's negative, when it's positive.
Well, because as long as we're consistent, it doesn't matter, right? And so positive, negative. In this case, right, I'm taking block 2 minus block 1. Just because it's cleaner. But it actually doesn't matter. Difference. Order of subtraction must be consistent. Off for that much. Say we've got a difference of 10 here, and then that means we've got a difference of 3 here. We think about the difference in the differences. 10 and 3 are quite different, right? -10 and -3 are also quite different. In fact, they're different in the same way, right? And so that's why it doesn't matter. But 10 and 3, I would say those differences are quite different. Whereas if we look here and we calculate the difference here, we can look at the difference in the blocks as well. And so let's see here, we've got the difference. And if I go 7 minus 5, just to use that same kind of layout, I get 2. And then 10 minus 15, I get -5. So here, there's a difference in the differences. And same thing here. 10 is different from 3, and 2 is different from -5. So I'll say down here, since 10 and 3 are different, right? Are different, and 2 and -5 are different. In fact, we only need one of these to be different, but usually what's going to happen is that both of them would be different to use an interaction. Right? And so since 10 and 3 are different and 2 and -5 are different, we suspect that we will need an interaction term. An interaction term. So there's an interaction effect if there's a difference in the differences. Okay. We can map this, right? If we graph So this is how we would do it numerically, right? We could check for interactions numerically. We could also graph this and look at it, right? And so what we're going to have is you're going to pick one of the factors and put on the x-axis, right? And so one of, with your levels on the x-axis, and then you're going to put the response on the y-axis, and then you're going to plot your means, right? Your means for each of these for the different treatments probably, right? If you've got your factors or your blocks on the x-axis, then you would have your different means and different colors probably for each of the treatments. And so what it's going to look like, so you've got this interaction plot. We can visualize whether we need an interaction term using an interaction plot. So on the y-axis, you're going to have your response, right? Your response variable, y, whatever it is. And on the explanatory side, right, you're going to pick one of the factors. So one of the factors. Doesn't matter which one, but if you have a factor that is ordinal, right? And so we've got this kind of ordinal nature, meaning there's some order, some natural ordering, whether those be measurements that we've converted into categories, right? Or if you've got groupings such as first year, second year, third year, fourth year, right? So if you've got some sort of ordinal levels, then put that as your explanatory, right? Because what might happen is if you've got some sort of natural ordering here, you might pick up on some trends, right? That you might not see if you've just got different, treatments or whatever, if they're not ordered. And so if you have, so just as a rule, you can use either of the factors, but if you have a factor with ordinal levels, so here I'll say, if you have a factor with ordinal levels, with ordinal levels, right? So some natural ordering. Use that factor on the x-axis. Use that factor on the x-axis. You might spot some trends, right? So you might see some trends going on. Start a sentence with because. I know you shouldn't. But there, I said it. So because we might spot trends, right? We might see some trends because we might be able to see some trends, right? Especially if you've got some sort of time variable, right? Over time, how are things changing, right? So there just might be more information in there. Like I said, it actually doesn't matter, but just to get as much information out of this thing as we can, right? There's some some rules. If both of them are ordinal, then of course, again, it doesn't matter. Pick one. Okay, so then what you're gonna have is, there we go, is you're gonna have the averages. So here is one of your factors. Let's say this is your blocking factor, for example, right? So if you think back to that table, each of the blocks had a mean value for each of the treatments, right? And so each of the treatments are going to be plotted, each of the treatment means in this case would be plotted above each of the blocks. So if we've got, just to say, if we let the blocks, which were blocks 1 and 2, yeah, makes sense if we're talking about kind of time series, right? Something like that. Who knows, right? But 1 and 2 I know is ordinal, so yeah, it works. I'm going to put the blocks on my x-axis and then the treatments on my y-axis, sort of. So here, I'll say I'll use my blocks which have factors 1 or levels 1 and 2. And so in this example, right, I'm going to have 1 and 2 here. And then let's use green. Or actually, for this example, I'm going to have my treatment. I've got treatment A and treatment B, which I'll make a little legend here. A and B. Because what I'm going to do is I'm going to plot the means on this graph. So for treatment A, in block 1, I had a mean of 5, and it looks like all my means range from 0 to 15. So just to get an approximate scale on here, now I'm not very good at drawing scales, so 5, 10, 15, ish. So I've got a mean of 5, and then for block 2, I've got a mean of 15 for my treatment A's. So here's my mean of 5, and then I've got a mean of 15. What we do to kind of see how things behave is we don't draw a trend line, we connect them with a line. So we're just going to draw a line between these two to see how they move, right? And of course, if we have more than 2 levels of the blocks, like I said, then we would just keep plotting this and connecting it with the line, right, to see how it behaves. But we're just focusing on the most simple case. So then for treatment B, I started with a mean of 7, and then I went to a mean of 10. So I started here at 7-ish, and then I went to a mean of 10. My lines aren't that straight, but I think you get the idea. So if we think about, if the differences were the same, right, then we would have parallel lines-ish, right? And so we can look at the numbers, that's fine, right? But often it's going to be easier to just visualize it, right? So if the lines that we find, and of course we can have more than just 2 treatments, we would just have more lines, right? Right? So we're just focusing on just the 2 by 2, but so if we have an interaction, then the slopes aren't going to be the same, if there's no interaction, you've got parallel lines, and so the slopes will be roughly the same between these two treatments. So here, I guess I'll put it down here. So if the lines are roughly parallel, we can conclude there is no interaction effect. Sorry about the lag here. Interaction effect.
This is all to know whether there is any time.
Yeah. That's all we're doing in this chapter, so we're gonna really hammer it home.
I'm like visualizing, so let's take the
Yeah.
choose regression over and over. So we have an over. We have multiple factors, and we have choose whether if there is an interaction. Have to do all these things, then an over.
But I mean, at the end of the day, if you just calculate the means of each of the cells and then plot them and look, and then you can just argue, okay, all the slopes are roughly the same. No interaction here, moving on, right? So we're breaking it down just to see kind of what's going on. You don't have to do the calculation of the differences and look at the differences. I mean, you will because you'll plot them, but that can kind of happen in the background. If you just look at the plot, show the plot, does it look like something's going on? Yes or no? Right. And then we'll introduce the interaction next day. But all the tools that we've learned so far stay the same. So if the lines are roughly parallel, we can conclude there's no interaction effect. But if the lines have different slopes, we should include the interaction effect in our model. We should include the interaction effect.
You do it by paintballing or
Yeah, basically.
yeah, slopes. So I was thinking
You would find the slope? I mean, you could, but eyeballing it is good enough. Right. We're eyeballing specialists. Here, if we see something like this, right? We've got this interaction. And so sometimes if we know about the data, right, if we know what these levels and factors are, then we can say, okay, well, I think the example that they start with in the textbook is if you're growing corn and you're adding, is it nitrogen? I don't know. You're adding something to the soil, but you're not adding any fertilizer. The plant will still die, right? And you only add fertilizer, but no, whatever the thing is, I can't remember, phosphorus, nitrous, I don't know, whatever. Probably not nitrous, but nitrogen, I don't know plants. But it needs to have two things to properly grow to make this, for the full effects of both the fertilizer and the, pretty sure it's, I don't know, nitrogen, something like that, right? And so it's got this interaction naturally happening, but this is how we would visualize it and just kind of figure out if there's a difference in the differences. Which doesn't make sense when you first say it, right? But then you start to think, okay, well, if the difference between block 1 and block 2 was the same for each of these groups, then from 7, I should have gone to 17. Right? Exactly, because then we would go parallel, right? And so we're allowing for changes between the 2 blocks, but if there's no interaction, then we would say that they should change by roughly the same amount, which they're not doing. Yeah.
The way we get the data, so for regular NOI, that one treatment, one block, one value.
That's right.
So when you're doing interaction, you have to have another set of data which has one treatment. For the same block, you have to have 5 values.
Yeah.
So data won't be looking the same, and you have to ask for the data to do the interaction.
Not sure I know. So
You need
yeah,
multiple observations to do interaction. But when you're doing simple NO, you have single data.
Oh yeah, so now we boil it down to the cell means, right? So you can replace those single observations with the means instead, right? And then you're back to single observations. But because they're means, we're able to establish if there's an interaction.
Here in this case, we are blocking, and in a single block, we have multiple observations. Take a mean of that. If ANOVA without blocking, this doesn't come into the picture.
ANOVA with blocking.
Yeah.
The way you get the data is one block, one treatment, one value.
Then you can't establish interaction.
Yes. So you can't establish the interaction.
No.
He has done the experiment 5 times for
Yeah.
the same blocking, for the same treatment.
Yeah.
Then you can do the interaction.
Exactly. Then you can check to see if there is an interaction. But the data that we're dealing with in chapter 6, for example, right, there's only one observation per cell,
Yes.
and then there's no interaction, right? Because the interaction requires that those cell observations are actually means, right? But then what we can do is then we can do the same thing but on the means, right, as we did in chapter 6.
If we have single observation, do we need to necessarily block?
Well, so if we think about here, right? So you've got 3 treatments and 4 blocks, right? What we were saying before is that we only have one observation, one. Now we're extending that and saying, well, for there to even be an interaction here, or for us to say that there is an interaction, we have to have multiple observations in each of these, right? But then we can shrink that down to just means anyways, right? And then we're back to the same case. But because they're means, then we can establish the interaction. But if we have single observations, right, and we ignore the blocks, then I would have 4 observations for treatment 1, right, if I ignored the blocking. And so
The first ANOVA will come.
say that again.
The first ANOVA will come into the picture. Like
One
you
Yeah,
just
the one
categorize
way I know that. Yeah, exactly. But if you have a block, use it, right? If you find that it's not needed, then of course take it out. But for us right now, we've moved into having blocks and using blocks, just kind of separating our data.
So that
And some people love it, some people don't.
So that means blocking comes into the picture, blocking and interaction comes into the picture. If we have heavy lifting to be done that with the observations. Not so many observations, you don't need to do blocking, right? You're just good with one way.
Yeah, it depends on how the
Yeah.
blocks behave, right? Like if,
No, even getting into the blocks. So let's say
Mhm.
the way we choose whether to do blocking or not
Yeah,
depends on how many observations we have or how we are trying to group them or put them together, right?
But sometimes, even if we have a small data set, right, if we can block them and extract some of that variability, right? So here, if we think about this and we exclude the blocks, right, and only have this one-way table, then, right, we would have 4 observations for treatment 1. But maybe what's going on is that the responses here are increasing as we move through the blocks, right? That could happen if we've got, now an example escapes me, right? But maybe this is over time and maybe things are just getting stronger over time. And if you ignore this, right, then our means, we might not be able to find a difference between these means because it's all kind of noisy. But then once we separate them into the blocks and say, okay, these are all from the first time point, these are all from the second time point, third time point, fourth time point, then we've pulled out a lot of that noise, right? And then we might be able to see some treatment effects. And so,
Like for a time series data, first 10 years a block, second 10 years a block.
yeah, you can use that. Yeah,
For decades data, every decade is every block.
you can do that. Yeah.
And for every treatment for that decade.
And so sometimes the blocks will kind of help separate things, and then it'll be easier to pick up on differences in the treatment, because they might get crowded if we ignore these blocks. Then what happens is the residuals have to absorb a lot of that noise. But if we're able to put that on the blocks instead, then we might be able to pick up on differences. So just like moving from simple regression to multiple regression, right?
Rather than normalizing the data because of its length,
Yeah,
probably break it into.
then we can maybe introduce another predictor, and things are kind of, then we're able to capture more of that variation. That's the same thing with the blocks. Your model is never going to get worse by introducing blocks. It might not improve, right? It might not make a difference, but it's never going to get any worse than from your one way. Cool. All right. What else did I want to say today? I really thought this was going to take longer. Great, hit me.
So let's say we are doing an experiment regarding drinking alcohol, and your blocks are water, Coke, and Pepsi, and you're doing it over the time.
Okay, yeah.
So the issue with doing over the time is the alcohol gives you have that. So
Yeah.
the fifth shot or something, it accumulates all the value of the 1, 2, 3, 4, 5 you're way drunk.
That's right.
Yeah. So let's say to normalize them and make it in a better way. Split. So I'll split the according to the time.
Okay.
So let's say for every 6 hours, I'll have 1 shot.
Okay.
After every 6 hours, so that the effect goes. So now.
Okay.
So now, if I want to do the interaction, I just want to put everything.
Yep.
So far, what I can do is all I can know is how difference is, how alcohol is reacting water different, Coke and rum, if there is any variation with respect to the human being.
Okay.
And and I want to know if the tax difference for male, female as well.
That's that we are complicated here. So let's say alcohol is the prime. So every treatment is alcohol with water is one treatment, alcohol with Coke is one treatment, alcohol with Pepsi is one treatment, and your blocks will be number of the time. So in that particular time, how many? So let's say if you're taking one peg in 10 minutes, or one peg in 20 minutes, one peg in 30 minutes will be your blocks. So you have to choose how many pegs in that time frame, because you have to, yeah. So again, how do you, again, male and female, that the
You can categorize.
you have to first filter out this data and then go to one rate after you get inference from this.
At the end of the day, the number of things that you can handle, right, on top of your response. So you establish your response, but the number of factors that we can handle so far, there are ways that we could add on more factors, but not a lot more without, completely overwhelming the model. It's just, we can have one thing with all its levels here and one thing with all its levels here. And so you don't want to overcomplicate things, because I'm hearing you've got your alcohol, your time, your gender, and your mixes, right? And so I'm hearing 4 things. You'd probably you could do the same thing, but you'd have to do the males and females separately. Yeah, so 2 separate experiments, exactly. Yeah, but then you can't really draw any inference between these two, because they're 2 different experiments. Overall, though, you could still do some stuff, but then I would take you back to maybe a 2-sample t-test, something like that. Between maybe one of the treatments, right? Focus on the treatments and compare those 2. But it gets very complicated very quickly, right? Especially when you want to introduce all those things. And of course, that's something that we do want to do, right? But we can, so far, what we're doing can only handle 2 things. So we would need to boil it down to 2 things, and then we can analyze it. Still going to be strong enough for most scenarios. And so here, right, we've got our blocks and our treatments, but that's it. That's all. Oh. But that's all we've got. Right. So if you had to choose, what would you put as your blocks and your treatments?
Time would make sense.
And I'm curious, what's your response variable? What are you measuring?
How
Okay. On a scale, on a categorical scale, or on a numerical scale?
I'll give some math problems to do or to identify something, and I will.
Maybe blood alcohol volume.
Or you can use the reasonable answer.
But I think those are kind of vague measures of your blood alcohol level, right?
Yeah, you should know that it's
We've all been signed up for this experiment, I guess. But remember, your response for what we're doing has to be numerical, right? And so if we're saying that our response, yeah, we can't, well, you guys can, because you've done logistic regression, right? But we haven't done it until after test 2. So we in this room pretending that we don't know that, right? But for us, the response has to be numerical. Response must be numerical. If it's not, then we need other methods, bless you, right? And then the blocks and the treatments, they have to be categorical, whether we've measured something numerical and we've made it categorical, right? That's allowed. Income brackets, for example, what's your income? That's a numerical variable. I can put it into brackets and make categories, right? And so we're allowed to take numerical variables and turn them into categorical variables, but we can't take categories and turn them into numerical variables. It just doesn't translate, right? And so these two must be categorical and categorical. We can turn, we can turn a numerical variable into, into a categorical variable. We can do that, but for how we set these things up, we have to treat them as categories. Who knew learning all those variables and all that junk that you spend the first few days in intro stats learning comes back up in a big way, right? We need to know how to talk about our data. And so, okay, so for your example, right, let's use our response is the blood alcohol level. What is that? I think it's BAC, blood alcohol content.
Know when you fall, you're down.
That's hard to measure. Blood alcohol content. And then your treatment. Mm-hmm.
Different types of alcohols. How can I write?
Yeah, so
Different
you,
types of beverages for a specific alcohol.
Yeah.
Because that will be more clear than so let's say if you have 4 different brands, if you want to mix everything up, you can't put, you have to have them individually, right? So how like how we look at for male and female. So you have 4 different brands.
but it depends on what you want to check,
I
right?
want to see how rum is affecting, how whiskey is affecting, how
But then-
beer is.
You can't.
You can't check them like on one person. If you have rum once and then you mix, you have another drink after that,
Yeah.
say whiskey. So you are basically checking the interaction that you have when you have rum and then whiskey. You're not checking them individually. Like as in, I have rum today, I have only rum shots.
That's the reason
It's
you have
different.
the time period to wear off.
It's
Okay.
So what you could do, you would have to simplify it, right?
Yeah.
But what if
So
you,
it's like 1 alcohol,
yeah,
like 60 ml, alcohol with water in 10 minutes.
mhm,
Your alcohol level in your blood is your numerical.
yeah. So this would be if you were testing the mixes, right? And
yes.
so, but let's say we ignore the mixes and you want to, and you're interested in, yeah, that would work, right? But then you would have to hold the amount of alcohol and the type of alcohol steady, right, in that situation. So it just depends on what you're interested in knowing about. If you're interested in, yeah, so if you're interested in the mix as the treatment, then you would use, you know, your water, your Coke, your orange juice, whatever, right? Red Bull, I don't know, right? And so those would be your treatments because that's what you're more interested in. But then, unless you make the amount of alcohol your blocks, which I don't recommend doing because that's makes it harder, right? Especially because you've got this. Presumably the same person would have to take 1 shot, 2 shots, 3 shots,
Yeah, people love it.
4 shots, right? So then you would have to hold the alcohol steady. Whereas if you're interested in the alcohol, right? So we've got vodka, rum, whiskey, whatever, tequila. Then we would have to hold the mixes steady, and we would have to kind of eliminate that as a factor, right? Unless that's something that we're interested in, right? Then we can make those our blocks, sure. But if you're also interested, if you're more interested in male and female effects, those should be your blocks, right? So it just depends on teasing out what is it that you actually want to know about. Like, what do you actually care about? Because we do have to boil it down to something like this, right? And so we can only vary two things. And so the two suggestions, right, are very different experiments, very different. This would be kind of when we're laying this stuff out, this is experimental design. Experimental design is its own field, right? It's its whole other beast. And can be kind of tricky, right? As we can see, right? Because, okay, I want to know about all these things and I want to later be able to compare, you know, these two groups. How am I going to do that?
If you want to block it gender-wise, probably have to boil down your data, like let's say 10 shots in 1 hour for male and 10 shots for female.
10 shots.
I'm giving you an example. In 1 hour, 10 shots for male and female. And for different. I'm just, let's not talk about possibilities, but let's talk about data. So let's say rum, 10 shots for male.
Can we say 3 shots?
Okay. Okay, 3 shots in half an hour.
Something reasonable.
3 shots in half an hour for male, 3 shots in half an hour for female. Rum, whiskey, vodka, and so on. That could work.
Yeah.
But
that's a nice clean design.
yeah.
Right.
Because you have to clean your data doing this analysis, because you can only measure 2 things. You can't put in time, you can't put in level of different brands, or you can't put in gender all together.
We can, so one thing that we can do, we should set this up before we do our experiment, right? We should have a good idea of the things that we want to be able to say, the things that we want to be able to compare, right? But of course, if we're choosing to remove the gender as a block, for example, if we're going to say, okay, I'm not actually interested in that, you would probably record it anyways, so you would have it. But one thing that you have to keep in mind is that, well, I didn't go into this, you know, randomly assigning males and females to different blocks, right? Or maybe not randomly assigning males and females to different treatments, I should say. Can't assign people to different blocks of gender, either or other. One or the other now. So, right, experimental design, can be tricky, but as long as you've got that information, you can still use it, but you're limited because then you might not have a balanced design, right? If you collected this data and you didn't really care about the gender, right, then you might have, 7 females and 10 males for treatment A, and then, you might have this unbalanced design, which, if we talk about comparing the interactions, right, if we're taking means of different sample sizes, then we've got different weights on these means. And so, right, one of the conditions for checking the interactions the way that we were doing was that we have a balanced design, right, have all these even things going on.
You designed this, you got the box plots, one is different from other 4 and 4 look same. You want to know how significantly different they are, and then you do the effect size. Now I understood why you are dividing the standard deviation. It removes the scale wise.
That's right.
Even if you're comparing the influence with mosquitoes, it scales it down to the same.
That's right.
Yeah. I got that after talking to you after half an hour. So now, how big is big enough in the effect size?
Well, the effect size, right, is standardized. So sometimes an effect size of, kind of 20% might be big, right? It depends on how lenient I want to be, right? Yeah, I don't know if I don't think I have a cut and dry. I feel like an effect size larger than 30% or 0.3, then we're getting somewhere, right? And I'm pretty sure there are levels, because who's the effect size? Is it Cohen's D? It's the distance, Cohen, I think it's Cohen. Anyways, there are established kind of guidelines. I think it's 0.3 to 0.5, 0.5 to 0.8, and then larger. But off the top of my head, I can't quite remember, but I mean, Google will tell you. So
In the lab task which we have done,
yeah,
0 minutes, we had effect size of 182%. DR,
okay, yeah.
right? We came down to 5 minutes. It got down to 50%, but it's a positive.
Mm-hmm.
So that means, the mean is like 50% so and so of this so and so standard deviation
right.
points, right?
Yeah.
So again, it came down to 30%, and then it got down to negative, if you guys remember, right? So are we summarizing the way it's going down, or are we doing it separately for each and every treatment?
You can do it separately for each treatment, or do pairwise effect sizes if you want to. But usually you would just drill down to the ones that you're interested in. Right? The effect size of this and this, or the difference between these two.
Because first thing, we had the minimum and maximum mean interval to choose whether it is significant or not, right? If they're intersecting or not.
Yeah.
With each other, like 0 to 5, we had 1 minimum maximum. 5 minutes, we had 1 minimum maximum. We'll see whether if they're interacting or not, intersecting or not. Then if 0 is not intersecting with anyone, we say it's not. It's significant.
That's right.
Right? The changes from 0 minutes to 5 minutes is significant.
Yeah.
But if everything is intersecting, we say, okay, fine. We have to look into it, but they're not that significant.
Yeah.
But
so if 0 is not in the interval, then you can say that, okay, there's something significant going on here, right? If 0 is in the interval, there's nothing significant
and
going on.
that significance relates to significance of the percentage of metamorph or whatever the term is.
Yeah.
Right?
Yeah. So it'll relate to well, you're comparing the individual amounts as a difference, right? So, and you probably haven't done that in your ANOVA output. And so that's just one way to be able to compare all these levels. Yeah.
And our interval, by our interval, we chose whether it's significant or not. And then we calculated effect size, right?
Yes.
First we
for
had
the differences?
Yeah. First we had upper limit.
You can do it for the individuals too, but probably for the differences.
First we had intervals like upper mean and lower mean, and we chose whether significant or not, depending on the intersection of those intervals. And then we calculated effect size. So effect size we wrote so and so percentage of mean is changing in the standard deviation points. And what does that tell about your analysis?
What does the effect size say?
Yes.
It tells you whether that difference that you found, so even if it's a significant difference, it might not actually matter when you apply it to something, right? So for example, because I taught the stats for nursing last term, so they had a really good example where, okay, so you hired this consultant and he came in and he said, oh, with this new method, I'm able to improve your waiting times significantly. And someone's like, okay, well, significantly, that's great. So how much time are we saving? And he goes, 2 minutes. And they're like, why would we buy something? That difference of 2 minutes might be significant, right? Statistically significant. But when you take into account the variation in the wait times, right, 2 minutes, the effect size of that is not going to be very large, right? And so even though we were able to tease out a difference in 2 minutes here and call it significant, right, probably because we've got huge sample sizes or whatever, we were able to pull out a significant result. But when we take into account the spread in the wait times, you know, people are waiting between probably, you know, a minute to 45 minutes or probably longer, right? And so when we take into account that spread, that 2 minutes, there's no, the effect size of 2 minutes, it's going to be very small, right? And so, so we can get a significant result and have a pretty small effect size still.
Okay, so your effect size defines what's the wait time, and your intersection of intervals say whether it is significant or not. I mean,
That's
the
right.
wait time is significant.
Yeah.
So
For the difference in wait time.
your 2 minutes can be significant, or your 10 minutes can't be significant, right? Depending on.
Yeah, it just depends on your data. It
Yeah.
depends on, you know, how your sample size usually, right? To get a significant result of a difference of 2 minutes, I'd have to have a really large data set. And so there's kind of cautions around huge data sets too. But yeah, so the effect size takes a step back and says, okay, so what, you found a significant result. Does it matter when I compare it to how other things behave from this sample, right? And a small effect size says, no, it doesn't actually do anything for you, right? Does this result matter? No, not really, right? And so that would give you a small effect size. Oh, that's my time, I guess. But yeah, so that kind of, I know effect sizes are kind of tricky, right? It's possible that we might have an insignificant result, but it could still have a large effect size. Very, not likely, right? But you can check effect sizes, and sometimes you might be able to find, okay, well, that was a large effect size, and maybe, you know, it wasn't quite significant, but maybe it was borderline. And so then you would still care about those results. But I would say, no, you test for significance, and then you check your effect sizes. That's what I would say. All right.